right, day 6 of Math History Notes. Woohoo! Here's what we're going to talk about. We've been looking at the Greeks, different famous Greeks. We started with Thales and Eratosthenes, and I think the last time I taught, I said maybe you should go look at Pythagoras. So Pythagoras is a pretty well-known mathematician from historic days. He's an ancient Greek guy. And the interesting thing about Pythagoras, I think, is most people know the Pythagorean Theorem, right? It's named after him. However, we already know from the Plimpton 322, that clay tablet, that the Babylonians had knowledge of a squared plus b squared equals c squared. And there's evidence in Chinese scrolls and such that the Chinese had that relationship. So he's certainly not the first one to find it. We're not even sure if he or his followers actually proved it first. We don't even know that. I think that the reason he gets it is just for sheer number of followers. So he had a group that was called the Pythagoreans. And these were followers of Pythagoras. He started a school in what is currently Italy, but back then was Greece. So that's why he's in our Greek section. Okay, so his school was very mystic, and it was the thing of legends and superstitions and stuff like that. So what I mean by that is there are a lot of stories about Pythagoras and his followers, and I think that that's one of the reasons why like a lot of people know the name Pythagoras. They just really, he captures the imagination, so all the legends and things like that. So here are some things that they did. He had a school. It was originally set up for discussing politics and religious beliefs. And then what happened was they got a little cultish. So they had secret induction ceremonies. They had secret handshakes. They had things that they could not eat. They had rituals. They loved the triangles, but they also loved the 5-pointed star. So they would wear patches on their clothing that had their symbol. I'm sure it looked a lot nicer than mine. But patches on their clothing that carried their symbol, so that if you saw them in town and you saw somebody wearing a patch, you would know, hey, that's my fellow Pythagorean. So they had little emblems and stuff that they would wear. They worked in communes, so communal living. They had rituals, for lack of a better word. For instance, don't walk in the bean fields. Or don't cross the road after 5 o'clock on the Sabbath, or things like that you could or couldn't do. There were people who would take vows of silence. So for long periods of time, just couldn't talk. While they were doing that, they were supposed to be studying and communing with nature is a big part of what they did. And for them, nature was number. In fact, numbers represented everything. So for instance, they had a number that was for the universe. I think it was 6. I'm not sure about that. I don't remember exactly. But they had a number for men. They had a number that represented women. I don't remember which one was even and one was odd, whichever one was which. They believed in reincarnation. They believed in studying your habits and patterns and making yourself better. One of the things that they did was that we know of, one of the first people that studied the math of music. Okay, so what we mean by that is whenever you're playing music, there are certain notes that you can play together and they might form a chord. Or something might go together and make harmony. Okay? However, if you push the wrong buttons, say on a piano, the wrong keys on a piano, you might get something that kind of reverberates against each other, sounds like, and that would be discordant. Okay? So, which nowadays we would call that discord. Okay? If you are not syncing well with somebody, a friend or something, you might say you have discord between the two of you. So that's what's going on there. Basically what they're doing is they're studying the waves, sound waves, and vibrations. So for instance, somewhere, you can probably look on the YouTube channel for A&M Commerce, there is a video of Dr. Anderson playing the banjo. If you've never seen him, he's amazing. And he's discussing the difference in octaves. And so he's got a string on the banjo, and he's like, okay, if I put my finger here in the middle, if I just pluck the chord, the string normally, and then I put my finger in the middle, and then I pluck half of the chord, it's exactly an octave higher because the string is shorter. That means that the sound waves are working through their cycle faster than if they have to travel the entire distance of the string. Twice as long, twice as low, twice as short, twice as high. So you have octaves, you have thirds and fifths. So they really studied what is it that makes things be in chord, in harmony, and what is it that makes things not in harmony. Okay, so that's one of the things. They thought that the world was a ball on a string. So interestingly, that lets us know that they thought the world was a ball, so they thought we were round. They knew we were round. They did not think it was a flat earth back then. Okay, but the other thing is that they thought it was on a string, meaning that they thought it was orbiting somehow, right? So if I hold the string in the middle and the ball goes around on that string, then it gives me some form of an orbit, which is kind of interesting for 300 BC, 500 BC. Pretty interesting. And they called the universe the music of the sphere, meaning that they thought that there were a lot of balls in the universe rolling around and doing stuff. Like the Babylonians and the Mayans, they tried to explain the phases of the moon and things like that. Why is it coming up in different locations at different times? Why is it a full moon? Why is it a new moon? And those kind of things. So I think, though, that the interesting thing is what we know them for is the Pythagorean Theorem. However, they didn't do much with the Pythagorean Theorem. We'll do a proof or two of the Pythagorean Theorem in a second. But they didn't do a lot with the Pythagorean Theorem. But what they did do is they came up with a bunch of numbers that we would now call like Pythagorean triples is what we call them now, like the 3, 4, 5 triangle. Okay, and what we know is that if a right triangle has leg length of 3 and leg length of 4, then the hypotenuse is going to be a 5, and these all come out to be really lovely whole number answers. And so that's kind of what, like, if you looked at the homework on this section, there was some stuff where we talked about the Babylonians and how they did different things, and different columns that were basically the Pythagorean theorem, and they're using whole numbers, right? So if I square this whole number and I square that whole number, can it add together to give me the square of a whole number? So that was the kind of thing that they were looking at. But what the Pythagoreans realized was, if I have a triangle whose sides are, for instance, 1 and 1, and I use the Pythagorean theorem, 1 squared plus 1 squared is 2, and then that would be the square of the third side. That means that the third side has to be the square root of 2. So if we're looking at that and we say square root of 2 for the side C, the problem is, how do I measure something that's square root of 2? So if I have something that's a unit, 1 unit long, say this is a unit long, that's fine. I can double it. I can duplicate it, right? This would be a unit long. That gives me this entire distance of a 2. That's great. But how do I make root 2? And we know nowadays we would call that an irrational number, right? Okay, that's a problem for the Pythagoreans because all the things that they wanted to measure were in whole numbers, and they didn't know what to do this. They actually call it a crisis of number. Okay, this is a crisis, and believe it or not, people are like killing themselves over stuff like this. Oh my gosh, what am I supposed to do with the square root of 2? Basically, they thought that they had broken numbers because they came up with irrational numbers. So actually, I would say that the number one thing that the Pythagoreans did for us is come up with irrational numbers and try to resolve what you can do with them. Okay, so we've got square root of 2. What do we do about that? And how do we write it? And how do we work with it? Because, oh my goodness, what are we going to do with that? So it is a direct response to the Pythagorean theorem. However, it's not like this brand new mathematics that they did. The second thing that they did was they looked at triangular numbers a lot. And we'll talk about those in a little bit. So those are their two kind of big contributions to math, and they really don't have a lot to do with the Pythagorean theorem, except that they were using it whenever they kind of broke ground on the irrational numbers and said, oh my goodness, what are we going to do about that? So I normally, if you were in my face-to-face class at this point, I would say, have you ever proven the Pythagorean theorem in any of your classes? Yeah, so sometimes we are required to do that. And there are proofs out there. There's a lot of proofs out there. So just by a guess, I would say, my goodness, are there more than 5 proofs of the Pythagorean theorem out there? More than 50? More than 100? More than 200? There are over 300 individual proofs of the Pythagorean theorem, which in itself is amazing because normally any old time we want to prove some theorem, we get one proof, we're like, oh, done, that's awesome, we proved it, we move on. You might have something that's like proof by contradiction, and you might have a direct proof, but you're not going to have 300 proofs of pretty much any theorem that we explore. But the Pythagorean theorem, for whatever reason, because it's accessible to people, because young kids play with it, I don't know. People just play with it, and so it inspires people to actually play with numbers and learn stuff. Maybe it's because the concept is pretty easy, right? That right triangle, everybody can do it. Maybe that's why. I don't know. But it seems to really inspire some people. So we're going to spend a little bit of time looking at a proof. There are some purely geometric quote proofs, things that you could do with younger kids, like whenever I teach middle school math classes, I teach them, and I'll put a thing on D2L. So if you look at it at a triangle called ABC, it's a right triangle, and you just talk from a purely geometric standpoint about ABC. Whenever we talk about a squared, in the olden days, when they mentioned square, they literally meant we're going to make a square out of that guy. So this would be the square whose side is A and the other side is A. So for us nowadays, we call that a squared, and we just go on. A squared, yay, easy peasy algebraic notation there. But back in the day, they literally meant, like, this is a plot of land. One side is 5 feet long and the other side is 5 feet long. So it's 5 square feet. That's literally what they meant. Like, you could mark them off in there. So when they do the b squared, same deal. And like I said, I'll load this up so that everybody can play with it if they want to. So I've got a squared plus b squared equals c squared. So we'll have the same deal going on over here. Of course, it's going to go off my page. But I'll have a square over there. So the idea being that physically these two squares add up to give me the larger of the three squares. So the idea would be, for a middle school proof or young kids or something like that, if I take this b squared and I take that portion out of the c squared, and then I start cutting, should be a square, so they should be equal looking on both sides, and then I start cutting this a squared into, say, strips, I should be able to cut it into strips and take that strip and fill in. And cut this guy into a strip and take that strip and fill in. And eventually I should be filling in all of the blank spaces over here until the entire area of the c squared is completely filled up with a squared and b squared. So one of them you're going to have to slice up and fill in the gaps, but if we did it right and we were precise enough with our measurements and our cuts, then we should be able to fill in. So it's kind of an interesting hands-on geometric proof, so to speak. Now we know, as adult learners here, that that's not much of a proof, right? So it's good for young kids. You can usually convince young kids if you can show them the same thing 5 times. They'll go, okay, it must be always true. Okay, but not quite good for a mathematician. So we're going to do a different one. But there's one. I'll stick that thing on online if you'd like to take some time to cut them up and play with them. You're welcome to do that. All right. We, however, are going to work with a proof that was done by President Garfield. So this is what's interesting about the Pythagorean theorem. It is so interesting to people that even presidents play with this. Okay? It just captures their imagination. What can I do with that? Can I prove it? And sure enough, he came up with his very own unique proof. So we're going to run through it real quickly and see what it looks like. Basically, if you read, Garfield kind of gave just a description of it. What he said was create a trapezoid, which a trapezoid is a quadrilateral with exactly one pair of parallel sides. So in general, we might draw it like this. This would be an isosceles, where the little chevrons mean those sides are parallel. Okay, these sides would be congruent. That would be an isosceles trapezoid, or some people might draw it as a right trapezoid, where these two sides are parallel and these angles are right angles. So it just depends on what kind of trapezoid, but the idea being there's only one set of parallel lines on it and the others are not parallel. So that's kind of the definition for trapezoid. So create a trapezoid that is made up of two congruent right triangles and one isosceles right triangle. So he's kind of forcing his trapezoid to look a certain way by giving these stipulations. Two of them are right and congruent, one is right and isosceles. And what his proof does is basically says, then compare the area of the trapezoid to the sum of the areas of the triangles. And there's different ways to draw this. If you want to stop the video and play with it a little bit and see if you can come up with a trapezoid that's made up of two congruent right triangles and one isosceles right triangle. then go ahead and play with it for a second if you want to. I think it can be difficult to visualize without the picture, so I'm going to go ahead and put one in. So basically, and there's different ways to draw it, but mine normally looks like this. It's kind of a tall, skinny, scalene triangle, right triangle. We'll call this short side A and the long side B. Of course, the hypotenuse is always C. And then they lay that triangle on its back, basically. And have him over here, A, B, C. Okay? So that those are supposed to be congruent. They're not quite exactly the same, but they're close. So we can see the A is the same A, the B is the same B. So those are congruent. And then they just drop the, connect these 2 points, basically. Drop that, it's not quite a, I don't know what you'd say. Drop the side of that trapezoid, okay? Now the idea being, because this is a right angle over here on the right-hand side, and this is a right angle over here on the left side, and the base here, or the side, the length A plus B here, is all connected, that these must be 180 degrees from one another, which means this side B is parallel from this side A. So it is a trapezoid, it's just that instead of the bases being on the bottom and the top, they're on the sides in this case. So if you don't like it, you can turn your picture around so that your bases are on top and bottom, whatever you want to do. So, but it's definitely a trapezoid. And then we see right here, this guy in the middle is an isosceles triangle, C and C. And we don't know what that long distance is there. It's going to be a D or something like that. But he's saying make that isosceles triangle in the middle be a right triangle, because it's in his definition. It's going to be an isosceles right triangle. Okay, so what that means for me is, like, say if this little bitty acute angle up here is 30 degrees, then that would make this angle underneath the right angle 60 degrees. And this straight line here would then make this little angle be 30 degrees, that matches with up here, and that makes that guy be 60. So it makes sense, and it all adds out, so yay. All right, so he says, look, you got to have this particular picture, and then we're going to work on the area of the three triangles, and the area of the trapezoid, and we're going to set them equal to each other. He says compare the area of the trapezoid to the sum of the areas of the triangles. So the area of the triangles, we know area of a triangle is 1/2 the height times the base, right? So here's this scalene triangle here. The height is B, the base is A. So area of triangle number 1 is 1/2 A times B. Okay, I'll call him triangle number 1. Let's go ahead and call the other scalene right triangle triangle number 2. Area of triangle number 2 is also 1/2 of A times B, because they are congruent. Which leaves me with triangle number 3 up here. And if his height is C and his base is C, then the area is 1/2 C times C, or C squared. All right. So there's my 3 areas of triangle. I need to sum those all up. So the sum of the area of the triangles is 1/2 AB plus 1/2 AB plus 1/2 C squared. I'm going a little bit fast. If you need to stop and pause the video and go back, it's fine. Okay, whenever I clean that up a little bit, these will combine. So I get AB plus 1/2 C squared. That's that area. All right, so there's the first piece. Yay. Then I need the area of the trapezoid. Yay, so we need a formula for the area of the trap. And I know everybody has that formula for the area of a trapezoid right off the top of their head. They can just spout it out, right? Yeah. So, the idea of the trapezoid is It's actually similar to the area of a parallelogram, but instead of you just have the bases of parallelograms would be the same. Here my bases are two different sizes, right? The B is definitely longer than the A. So instead of just saying half of B squared, or B squared, height times base, instead of doing that, I'm going to have to average these two because they're not exactly the same base. Like if it was a parallelogram, those would be exactly the same base, right? So the area of a parallelogram is height times base. Length times width, however you want to think. Like rectangle is length times width and all that. So those are the same. So this is the same except for B1 plus B2 over 2 is what we're going to do. You average the bases because they're not the same length. So it looks a lot like a parallelogram, but it's not, because those bases aren't the same length. We have to average them. Okay, so the 1/2, it's in the formula, divide by 2 there. The base 1 is B, and base 2 is A, so that's A plus B, because I'm adding the two bases together. That's this piece. And then the height here, remember heights are always perpendicular, right? So again, if it bugs you, if this is my base, the height is this entire distance here. And so that height is A plus B. Okay. Which turns out to be 1/2. When I square that guy out, it's A squared. AB plus AB is 2ABs. Plus B squared, and then I'll multiply through the 1/2. So this is 1/2 A squared plus 1/2 times 2AB. Those are going to reduce out, right? It's just going to be AB plus 1/2 of B squared. Ta-da! Here's what it looks like. 1/2 of B squared. All right, so there is my formula for the trapezoid, my area of the trapezoid. So what he says is compare them. What he means is set them equal to each other and solve, right? Okay, so I've got AB plus 1/2 C squared is equal to 1/2 A squared plus AB plus 1/2 B squared. They've got to be equivalent, right? Because this trapezoid is these three triangles, like they're the sum of the parts, right? Makes up a trapezoid. So they've got to be equivalent. So he sets them equal to each other. And then he says, oh, look, I have an AB on one side. I can get rid of that because there's an AB on the other side. So I've got 1/2 C squared equals 1/2 A squared plus 1/2 B squared. And look at that. They all have a 1/2. So if I just multiply by 2 on everything, then the 1/2s will drop out, and ta-da! We have a president who can prove the Pythagorean theorem. Do some math. Look at that. It's really kind of cool. So here's what I'll say about that. I really like the President Garfield proof, so maybe you should be familiar with it. Say whenever we have a test in 4 weeks. I know it's kind of a ways off, but it's coming up. You will also perhaps want to make sure that if I start you on a proof and point you in the right direction for proving the Pythagorean theorem, that you can kind of go, okay, I see what's happening there, and just follow it on through. So it's not too terribly bad. So that's not bad. We can do one of those. It'd be awesome. All right. Well, I said there were two things that they did. One was irrational numbers, and one was triangular numbers. So let's take a look at triangular numbers. So that's all I'm going to do with Pythagorean theorem. You can take a look inside of your book, your readings. There's a PowerPoint on Pythagoreans. Take a look. Familiarize yourself with proofs and things like that. But we're going to move on. All right. Triangular numbers, for whatever reasons, triangles really fascinated the Pythagoreans. So whenever they started looking at triangular numbers, is like, what's going on in here? They're actually kind of cool, and later we'll see how some stuff developed for Carl Friedrich Gauss, but he doesn't come around until the 1700s. So we're still 500 BC here. So we don't have the benefit yet of his methods, unfortunately. So the idea behind triangular numbers is that you take dots, and they're trying to figure out how many dots we can put together and make a triangle around it. So you want the dots to be inscribed in the triangle. So for instance, 1 is the nice initial case, the kind of boring case. I can draw any shape around 1 dot that I want, right? So triangle for sure around that one. But then they said, hey, look, what if we took 1 dot and then underneath it we added 2 dots? So the second row of dots here, we just add 1, is what they're thinking. Well, that makes a triangle also. Okay. So then what if we had this triangular number, 1 dot and 2 dots, we already found him, and then we add another row of dots underneath it, but we add 1 to that row of dots. So it would be 3 dots. 1, 2, 3. Well, that makes a triangle also. So they're just kind of playing with this kind of figure to see, hey, here's my pictures, my pictorial. I've got 1 dot, I've got 2 dots, I've got 3 dots. Next I would add 4 dots. And sure enough, that also makes a triangle. And so they quickly see, hey, we've got a cool pattern going on here. We can see exactly what's going on as far as adding 1 to make the next row 1 more. So the next triangular number would have 5 dots on the bottom row and then 6 dots and so on. So this actually creates a really cool sequence of numbers. And for sequences, there's two kind of things we need to keep up with. One is the index. So the index or the figure number, depending on how you were taught, tells me which term I'm on. Okay. Okay. But the actual term is its own number. So sometimes whenever people are playing with sequences, they start getting these two confused. Okay, so for instance, if I was looking at these, I would call this triangle number 1, so he would be T1. That's my first term. This would be triangle number 2. It's the one with 2 rows of dots. He's my second triangle, so T2. T3, T4. This is my 4th figure. We can talk about which figure number we're on, which index number I'm on, those kinds of things. So 1 is just, hey, where am I in my sequence? Like I'm just finding a slot that I'm filling in, okay? So that tells me my sequence number, my term number. But then the other is, well, how many dots is that? Okay, so the first triangular number is actually 1, because it's 1 dot. And the second triangular number is actually 3, because there's 3 dots. And then 6, and then 10. And if I had drawn out the next figure, I would have added 5, so it would have been 15. And so we have this lovely sequence going on of triangular numbers. And it actually comes in later, by the way, you may see it in Pascal's triangle. The same exact sequence comes up again and again. It kind of sticks with us for a while. 1, 3, 6, 10, 15. To get the next one, I'll add a 6 gives me 21. Add 7 gives me 28. I want to add 1 more. 8 gives me 36. So literally, I'm just adding. 1 plus 2 plus 3 plus 4 plus 5. And these are just consecutive whole numbers that I'm adding on, right? Or integers, depends on how you think of them. Positive integers in this case, if you're thinking integers. Okay, so what we're literally asking, what the Pythagoreans were literally asking 500 BC is, how can we look at these numbers in the sequence and produce the next one? Well, the next one's easy, right? So if I want to do 36 and add 9, I'll get 45. That's easy. And then 55 and so on. So recursively speaking, it's easy to figure out. Recursively means look at the term before, right? So if I want t sub n then what I do is I look at the guy before it, t sub n minus 1, okay, and I add to it whichever number I'm on, n. Okay, pretty okay. So if I want t sub 5, I look at t sub 4 and I add 5. Okay, well t sub 4 was 1, 2, 3, 4, 10 plus 5 gives me 15. Sure, it works. Awesome. Okay. So that's cool and that's lovely until I get to the point where I say, hey, let's find t sub 50. Because t sub 50, if I'm using a recursive formula, says, well, find t sub 49 and add 50. But I don't know what t 49 is. So to find t sub 49, I have to find t sub 48 and add 49, and so on and so forth. So in order to use this for a recursive formula, I'm going to have to find all 50 to get to t sub 50. And that really stinks, and I don't want to. Okay, so that becomes a bit of a problem. So that's where we'll kind of skip ahead a little bit, and we'll use a little bit of Gaussian knowledge, which Carl Friedrich Gauss, like I said, he's like my favorite mathematician ever. I wrote my master's thesis on him, dang it. He doesn't come around for another 2,000 years after this. But we'll use a little bit of his knowledge. So what Carl said was, and you can do this same kind of idea with young kids. There's this idea about a grocery store if you were stacking boxes of cereal to make one of these triangles that stands in the aisleway. You'd have 4 boxes on the bottom and then 3 boxes on top and that kind of thing. Okay, so he says, look, if you want to do that, and there's a big long story, we'll get to that later. But if you want to do that, what you need to do is you need to add the first term and the last term. Okay, so let's say that we don't want to do 50, but let's say 1, 2, 3, 4, 5, 6, 7, 8. Let's say I want to find a general formula, or a closed formula, sometimes it's called, for t sub 8. Well, we happen to know t sub 8 is 36. Okay. But I don't know that off the top of my head, so I'm going to do the whole add up. 1, 2, 3, 4, 5, 6, 7, 8. If I can do that mathematics, then I can find t sub 8. Okay. So what Carl Friedrich Gauss said was, look, we don't have to mess around with adding to get up to however many numbers. Instead, what he wanted to do was pair these guys up. So he sees that, hey, if I add the first guy plus the last guy, I get a 9. And then if I move in 1 on the bottom and in 1 on the top, I'll have a 2 plus a 7. And when I add those, I get a 9. And if I move in 1 more, I'll have a 3 plus a 6. And when I add those, I get a 9. And 1 more pair here. When I add a 4 plus a 5, I still get a 9. So what he said was, if you always add the first plus last, then you'll get a set number, whatever that number is, and it depends on how high I'm going here. So first plus last, that's how I'm going to get my total sum each time. Sum of the pairs. And then he said, but I also know that I have a certain number of pairs. So for instance, here there are 8 numbers. If I pair means 2. So if I pair those up, I've got 8 numbers. I'm going to have 4 pairs, right? 1, 2, 3, 4. Okay. So the number of pairs is going to be your total n divided by 2. Okay. So in this case, the sum of the pairs for us is 9, because we added. Okay. And then there were n divided by 2 of those, so there's going to be 4. Okay. And then I just multiply. So 9 times 4 gives me 36, and I'm out of space on this page. But it gives me 36. And lo and behold, that was the 8th number. T sub 8. 9 times 4. Look at that. Okay? So it works. And Carl said, hey, we can always do this whenever we're adding consecutive numbers, which is really cool. Okay? So he figured that out. He's really young, and then he found a formula for it. So we're going to use his numbers, his formula, and we're going to see it. We'll also kind of prove, so again, remember Carl didn't come along for 2,000 years. So we'll also figure out the way the Pythagoreans did it, because we're pretty sure that they had his formula. They just didn't have like the algebraic mechanism to write it down yet and see what was going on. So I'll show you that in a second. So what Carl said was, look, it's really easy. The first number is always a 1 when we're adding consecutive natural numbers like this, right? Okay. The first number is always a 1. The last number is always my n. Whenever I pair those together, it's 1 plus n, right? And I add 1 to the bottom, and I subtract 1 from the top, so it's like a plus 1 and a minus 1. So this is also going to be 1 plus n, and that's going to be 1 plus n, and that's going to be 1 plus n. So I'm always going to get 1 plus n. That's what he said. And then the number of pairs is always going to be the n divided by 2. So all he said was, look, if you want a t sub n, then what you're going to do is you're going to take your n plus 1, and you're going to multiply it by n divided by 2. Which is really cool, because if n is even, then n plus 1 is odd. But here the n over 2 is going to reduce, so that's an even number, or a whole number. Okay, it's not a weird number. And if n is odd, then n plus 1 is going to be even. So this will reduce with the 2 over here. So it's still going to give me a nice, pretty whole number. So it's kind of cool. So there we go. That's the Gaussian formula. Gauss's formula. And we'll see it pop up throughout the semester. We'll do different things with it. So be aware he's out there. It'd probably be on a test somewhere if you needed to see it. I'm not necessarily expecting memorization on this, but you should be able to see it, recognize it, and then use it. So there you go. All right, so that guy's out there. Now what we think is this. I'm going to steal the T3 guy because he's easy for me to work with. If I had the T3 guy, and it's making a lovely triangle here, what we think the Pythagoreans did was said, hey, this is a triangle, and it's half of a quadrilateral. Okay, so half of a quadrilateral means that somehow, and there's different ways to draw this, but somehow I ought to be able to look at this. Maybe it's a rhombus. My picture's terrible. But I ought to be able to duplicate that. And so I'll put 3 dots, and then 2 dots, and then 1 dot. Okay, so basically I took this original triangle and inverted it and slid it over, and there it is. Maybe we rotated it. Okay, so there's 6 dots over here, there's 6 dots over there, so the triangle is indeed half of that guy. Okay, so that's kind of the idea that they had. Well, if I'm doing that, then it's kind of a weird idea to double and then half it again. But if I'm doing that, then I will create something that's an array of dots that is 4 across and 3 down, or 3 slanted, however you want to think about that. So if I do that each time here, this becomes the 3 dots plus the 1 dot. Or if I looked at the bottom guy, that's the 3 dots plus the 1 dot. Okay, so the idea here being is, okay, so what I've got in this T3, whenever I double it, is a 4 by 3 array of dots. Okay. Rhombus of dots, however you want to think about that. That's 12. So the entire quadrilateral worth of dots here is 12, but I only want half. Okay. So we think that they really actually kind of had this idea, because what they've got here is exactly what Carl Gauss had. This is a 3 plus 1, and I'm looking at the third case, right? It's a 3 plus 1, and this is a 3. So this is my n plus 1, there it is. And this is my n, there it is, all over 2. So we really think that they actually had this concept, they just didn't have the algebraic mechanism to write it yet. It's kind of cool. Kind of neat for 500 BC, just saying. All right, so there's that. So what happened is that the Pythagoreans could actually then expand this, and you might see in your homework sets where they talk about other kinds of numbers, square numbers, pentagonal numbers, hexagonal numbers, things like that. So we're going to talk just a tiny bit about square numbers. I'm not going to get much into pentagonal numbers, but I will say, like if you wanted to create a pentagonal number, you might do, of course, I can draw any shape around a 1 that I want to. Okay, so there's always the 1, that initial guy going on there. But you might create something that looked like this to make a pentagonal number. Right? So you might be able to think about him as some kind of a triangular number plus a square number. So it's one less triangular number, but this is the second square number, right? So then you could add the second triangular number plus the third square number. Or if you didn't want to do it like that, some people will actually make it this triangular number and then do a rectangular number. So you can do stuff like that. So there's stuff out there, pentagonal and hexagonal and octagonal and all kinds of numbers. But we're just going to do square and be done with it. So 1. 1 is a square number, of course, because I can draw a square around any one single guy. But the second square number is what? We actually know these. These are not trick quiz. I know, right? Like we're used to, oh, square numbers, that's easy for us, but we're going to see how they developed it. So second square number would be a 2 by 2 square, right? If we're talking dots still. And the third one would be a 3 by 3 square. I'm just going to draw a few of these. So there is a thing in the PowerPoint online where some of these pictorials are in there to help see what's going on. That's more of a rectangle than a square, I'm afraid. 4 by 4. Sure, it's a square. Honest. Okay. So now we'll be doing square numbers, so they're not T subs, they're S subs. Square number 1, square number 2, square number 3, square number 4. It's still a sequence of numbers. Okay, so this is 1, this is 4, this is 9, this is 16. Of course, we as mature adult learners in the 2000s know that the closed formula for this, we actually know this closed formula to begin with. S sub n is going to be n squared. We know that one. Okay, so that's easy for us because we're very used to that n squared notation. But we'll figure out exactly how you would come about that in a minute. Okay. What I find interesting about this one is the recursive form of it. So to get the recursive formula for this, what I do is I have 1, and to get to the 4 guy, I add 3 more dots, right? From the 1, like I could kind of square off that guy if I wanted to. So there's S1, 3 more dots. So add 3. And then here, to get to the 3rd guy, here's my 2 squared, right? I would add 1, 2, 3, 4, 5, plus 5. And then to get to the 4th guy, let me pull out the 9 guy, 3 by 3, I would add 3, 6, 7. So we very quickly see this lovely pattern coming in that I'm adding odd numbers. The next one's going to be plus 9, plus 11, plus dot, dot, dot. Okay, so we see that going on, and what we say is, okay, if I want to get to the next one, I need to figure out how I can write that. So S sub n is going to be equal to, we know we're going to use S sub n minus 1 because we're using the guy before him. And then the cool part is we're doing odd numbers here, so there's 2 different ways I can write an odd number, right? It's either 2n plus 1 or 2n minus 1. So I need to figure out which one I'm doing. But yeah, so I say, hey, am I adding 1 or I'm subtracting 1? So what I look at here is to get to this second guy, look, there's a 1 coming off of this end, there's a 1 coming off that end, and then there's this oddball that's kind of in the corner, right? So I can pair up each side, so to speak. For the 2 by 2, there's 2 here, there's 2 here. Those kind of go with the side of the square that they're closest to, and then there's the oddball in the corner. There's a 3, there's a 3. Those go by the length of the sides, and then there's this oddball, okay? So it looks to me like 2 times 1 plus 1, 2 times 2 plus 1, 2 times 3 plus 1. So that's the nice, lovely recursive formula, okay? 2n plus 1, where you could kind of group those if you wanted to. So you know those are an odd number I'm adding. All right, well, that's cool. Let's see if it works for us. Let's do one really big that we haven't done. No, I'm kidding. Let's do 5, because 5 is easy for me to do. If I want the 5th guy, then I'm going to take the 4th guy, which is 16, and I'm going to add 2 times, I'm doing a 5, plus 1, which is 10 plus 1. Oh, this was 16. Okay. 16 plus 11. Sure enough. Uh-oh. Did I do that wrong? What did I mess up? 2n plus 1, 2n plus 1, 2n plus 1. I went the wrong way. How did I do that? This was the 4th guy. Oh, I know what I did. Because it wasn't 2n. It's right there is my mistake. I apologize. It wasn't 2n because this is my 3rd guy. It was 2n minus 1 because this was 2, right? 2 and 2. This is the 3rd guy. This is the 4th guy, but it was 3 and 3. Ha! Nobody yelled at me. N minus 1 plus 1. That's where it is. Yeah, that's exactly it. So, interestingly, what's going to happen here is even though I'm adding 1, whenever I simplify that bit, let me go ahead and do that. Oh, no, I'm sorry. I'll come back to this piece. I apologize. S sub n is equal to S sub n minus 1 plus, whenever I distribute this, 2n minus 2 plus 1. Look at what happens there. Because it's a minus 2 and a plus 1, all of a sudden, that gives me the other way, right? Negative 2 plus 1 gives me a negative 1. That's the other way to write an odd number, right? Yeah, there we go. Let's try it again. So S sub 5 equals S sub 4, but we said that's 16, plus 2 times n now is 5, and that's going to be okay because I'm going to subtract 1. So 10 minus 1 is a 9. There we go. So easy for us to check because we knew it had to be 25. So yay. Glad I didn't do a crazy number. All right. Good deal. Okay, so there's my formula for my closed formula. Well, that's my recursive formula, sorry. Okay, so what we want to know is how in the heck are they going to get a closed formula out of that? That's what we're looking for. So therein lies the fun part. We're going to, let me go back and kind of apply the Gaussian thing just a second. So we're going to start with the recursive formula with a generic, and then we're going to turn it into the closed formula. So it would look like this. 1 plus 3 plus 5 plus 7 plus da 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 da. Plus, okay, way over here, we're going to have, we're going to have 2n minus 1, right? And the guy before that is an odd number, which means it's 2 terms before him. So the one before that would have been 2n minus 3. Does that make sense? Because I have to go back to get the odd number before. So the one before him would have been 2n minus 5, and so on. Okay, so this is what it would look like as I just do this generically, which we're pretty sure the Pythagoreans didn't do that. So for sure they didn't have this formula, and they didn't have our lovely, notation. So, but whenever we do the Gaussian thing and we group these, the 2n minus 1 plus the 1, what happens is the minus 1 plus 1 goes away. That's just a 2n. Okay. And then when I group these, same thing, right? 2n minus 3 plus 3, well, that's just a 2n. So we're getting the exact same kind of Gaussian thing that we had before, which is cool because that's how we're going to know we're doing something right. But all of them, instead of giving me a particular number, because we're generic here, is giving me 2n. Okay? So all of my pairs add up to 2n. And then the question becomes, well, how many pairs? Well, it's the same as before, right? There's n numbers there, divide by 2. Oh, number of pairs, n over 2. So we're going to multiply it to n over 1 times n over 2 to get to my square number. Look at that. The 2's are going to reduce out. And lo and behold, n squared, which we knew. We knew that, right? We knew we were after n squared, but it's kind of cool to see how it just kind of, boom, there it is. It falls out for us. So kind of a neat thing that happens. Like I said, we're very sure the Pythagoreans didn't have that, but thank goodness for Carl Gauss in the 1700s, and he helps us out, and that is just lovely. So those are the two big things that the Pythagoreans really did for us. You can read through your notes, read through the book, read through the PowerPoints that I've got online, and that will help you. I think in your homework there are some proving questions similar to these. So it's stuff like prove that n cubed is equal to n times n minus 1 plus 1 plus n times n minus 1 plus 3 plus dot, dot, dot. So there's that kind of stuff, but it's going to be a similar process to what we just did for cubic numbers there. So kind of look through some of the homework, see if you can do it all. That'll be awesome. And I think that what that does is brings us up to date on everything that's online. There are some more Greeks that we want to get to, but my time is just about out, so I'm going to probably call it a day. Next time I'll pick up with Alexandria, which I think is chapter 4 in your book, but I'll go look and see and make sure. So we'll start talking about Euclid soon. He's a major mathematician for us. He did a lot of stuff, not just write the elements. He wrote other stuff, number theory and cool things like that. But as far as I'm concerned, we're done with the Pythagoreans. So yay, there's homework on Pythagoreans, I'm sure. All right, that's it. Have a good day.